Okay, so I found this problem in the Feynman Lectures in Physics exercise book, this one over here. There are loads of interesting problems in here, so I'm probably going to solve some of the most interesting ones and put them here on YouTube. So yeah, for this problem I found is basically a statics problem. As you can see, you've got a cone and there's a flexible loop of chain basically put on top of the cone and it's in equilibrium. It's also a uniform piece of chain, which means that the mass is evenly distributed. So if the total weight is W and these are the dimensions of the cone, basically the question is, what's the tension in the chain? I thought this was a pretty interesting problem because it's basically in 3D, so it's unlike some of the statics problems that you usually do, which are just masses on inclined planes and stuff. So yeah, I solved this problem and I'm going to show you how I solved it. There may be other ways of solving it that are more efficient and probably more elegant than this. If there are, then please leave them in the comments so I can learn something from it as well. So yeah, if you guys want to give it a go, please pause the video and try it out. And then when you're done, I'll basically solve it and show you how I did it. Okay. So for this problem, what I did was to basically break the chain into tiny little mass elements and just resolve the forces on each of the little mass elements so I could figure out what the tension needs to be to keep it there. So let's try that. So if you imagine just focusing on this one tiny little mass element over here, I'm going to shade that in. That mass element is going to be basically, if you add up all of those individual mass elements together, they should give you the weight W. So the way I'm going to define this mass element is to basically define it based on the angle that it subtends with respect to this vertical axis going through the cone over here. So I'm going to call this angle here delta phi. So I'm really thinking about an infinitesimally small angle over here, which basically means that it's a tiny, tiny mass element. It's not like some kind of big chunk of the chain. And based on that, we can basically call the weight of this thing delta W. So now what we really want to do is to figure out what the weight of this tiny mass element is if we know the tiny angle that it subtends with respect to this vertical axis. So what is delta W? Well, we're told that basically the chain is uniform, right? Which means that if we know that the mass is distributed evenly, then we can basically define what the weight per unit radian is based on the angle over here. So if we know what the weight per unit radian is, all we have to do is multiply it by delta phi radians, and then we get what delta W is. So what's the weight per unit radian? Well, okay, first of all, it's going to be the weight, the total weight of the chain, divided by 2 pi, which is the total number of radians in this entire circular loop. So now we have the weight per unit radian. Now if we multiply by delta phi, that's it, we've got delta W. This means now we can just start resolving forces on that tiny mass element to figure out what the tension needs to be in order to keep it there. So in these kind of diagrams, I particularly find it useful to draw the diagram from different points of view, especially because this is a 3D problem, right? So that's what I did. If you look at this cone and this tiny mass element from the edge, like from here, it's basically going to look like a mass on an inclined plane, right? With an external force, and that's going to be equal to the weight and the normal force and the tension. So let's draw that. If you look at it from the edge, it's basically going to look like this. And we know that the angle that this plane subtends with the vertical here, we can basically call that theta. So this is theta. And here's that mass element that I marked out earlier. And the weight of this mass element is going to be directly downwards, and that's delta W. And we know that the surface of the cone is going to exert a normal force on it acting perpendicular to the surface. So that's going to be, we can call that delta N. So I'm calling it delta N because it's only the tiny normal force on this tiny little mass element. Okay, cool. There's also going to be the tension on this tiny mass element. And the tension is actually going to be, it's actually going to be acting on either end of this tiny little mass element over here, so that it attaches it to each of the other mass elements. But in this edge view, I can only really draw one component of that tension, which actually acts tangentially, and that's going to be the horizontal component. So if we draw that like this, So this is really horizontal, and that we can call that component of the tension Tx to show that it's horizontal. Okay. Now what we've got to do is resolve the forces vertically and horizontally to figure out what the relationships need to be between these forces. So if we're resolving vertically, right, we're going to end up with the vertical component of the normal force balancing the weight. Okay, so, I mean, this diagram's not really being drawn that well, but you can imagine that the arrow of the vertical component should really be the same length as the downwards weight. But anyway, let's just carry on with it. So, if we want to figure out the vertical component, we need to know what this angle is over here. So using a bit of geometry, we can actually realize that this angle just so happens to be the same as this one here, so it's theta. That means that this component is going to be equal to delta n sine theta. So we know that delta n sine theta is basically going to be equal to the other vertical force, which is delta w. Okay, now if we resolve horizontally, a similar deal happens. When we look at the horizontal force, this is going to be equal to delta n cos theta, and that's going to be equal to Tx. So really now, all we have to do is figure out what Tx is in terms of the actual tension, and then we can basically solve this problem. But to figure out what Tx is in terms of the tension, we need to look at that geometry a bit more to realize what Tx needs to be. So again, I'm going to draw another view this time. Instead of drawing an edge view, I'm going to draw one from looking at the cone from overhead. So yeah, that's what I'm going to be doing. If you looked at the cone from overhead, you're basically going to be getting a circle, right? So it's going to look like a circle, and the radius of this circle is going to be equal to the radius of this bit over here. So we don't know what that radius is, but honestly we don't need to figure out, as you'll see later. So I'm also going to draw on that mass element, which is basically hugging the surface. So it's going to look like this. And I've exaggerated it as well so that I can label on all the forces quite easily. And we know that the angle that it subtends is delta phi. So as I said earlier, the tension forces are going to be acting on either end of this tiny mass element, because that's what keeps it connected to all of the other mass elements. And it's going to be acting tangentially like this, right? So in this diagram, because we're looking at it from overhead, we can see that this horizontal force that we're getting over here is actually made up by the sums of these two forces over here. So in this diagram, Tx is basically the sums of the vertical components of the tensions on either end of the mass element. And the horizontal force brought out by the normal component that's horizontal over here, that's delta n cos theta, that's going to be acting radially outwards in this overhead view. So now all we have to do is figure out what these angles are over here in order to figure out what these components need to be to add up to make Tx. Okay, so let's do a bit of geometry. So if we split this angle directly in half, we basically get this angle over here to be equal to delta phi over 2. So that means that this angle over here is also going to be equal to delta phi over 2, right? So now we know that this component over here is going to be equal to T sine delta phi over 2. So let's write an expression for Tx. Tx is basically going to be equal to T sine delta phi over 2. But that doesn't actually cut it, right? Because we got two of these vertical components. So we got to multiply the whole thing by 2. And at this point, we can actually also make use of a small angle approximation. If you remember, the way I defined this mass element was to basically say that the angle that it subtends with respect to this vertical axis, this angle, this delta phi, it's basically going to be so small that it's pretty much equal to 0. And we know that the sine of a small angle is basically roughly equal to its angle if you look at the Taylor expansion of sine. So we can roughly write this as 2t delta phi over 2. And if this triggers any maths people out there, it's not actually that bad, because this approximation becomes more and more accurate in the limit that delta phi basically tends to 0, which is really what we're looking at over here. So we're not committing many sins when we just write sine of delta phi over 2 equals delta phi over 2. In fact, it actually gets us closer to the answer as well. So we can cancel these 2's over here, and we basically end up with tx equals t delta phi. So now it's just a simple matter of plugging this back into the equations we got over here and eliminating the unknowns to figure out what t is. So now let's look at the two equations we got. We got delta n sine theta equals delta w, and we got delta n cos theta equals t delta phi. If we divide this equation here by this equation, the delta n's get cancelled. That's good because I don't know what they are. And the sine theta divided by cos theta gets us tan theta, which is nice because I can figure out what tan theta is from the geometry of the cone. So if we divide this equation by this equation, on the left-hand side we end up getting tan theta, and on the right-hand side we basically get delta w over t delta phi. Now we know what delta w is. It's basically going to be equal to the weight per unit radian times delta phi radians. This means that if we divide delta w by delta phi, we're basically just going to get the weight per unit radian, right? So because delta w divided by delta phi is the weight per unit radian. So we're going to end up getting w over 2 pi times the t we still have in the denominator. So t is going to be equal to w over 2 pi times cot theta. So cot theta is 1 over tan theta, and if we can figure out what tan theta is, we're good to go. So if you look at this, the cone over here, tan theta is going to be equal to, this is a right angle triangle first of all, and tan theta is going to be equal to the opposite side divided by the adjacent side. So now all we have to do is basically, to do cot theta, we just have to do the opposite, the reciprocal, so height over the radius. So if we plug that in, we're going to get WH over 2 pi r. So yeah, that's the expression I got for the tension, and it appears to agree with the one in the answers. If you spotted a mistake in my argument or reasoning, then leave that in the comments below. But if you found a more elegant way to get this, please also leave that in the comments below as well.